A Tuesday morning in Silicon Valley. Not an explosion, not a failure. A quantum computer found something so unexpected about the nature of computation itself that the team made an unprecedented decision. They shut it down. The real story is not about what broke. It is about what woke up. Picture a maze so intricate that no map could ever chart its turns. In classical computing, a traveler enters this maze and must pick a path, left or right, forward or back, one decision at a time. Each wrong turn means retracing steps. Each choice is a guess, and every possible solution is checked in sequence or, with enough travelers, in parallel. The process is logical, methodical, and always limited by time and brute force. Quantum computing rewrites these rules. Here, the maze isn't a puzzle to be solved by trial and error, but a landscape where every path is explored at once. A quantum bit or qubit doesn't just represent 0 or 1. It exists in superposition, both 0 and 1, until measured. The quantum traveler isn't a single explorer, but a cloud, moving through every corridor simultaneously. This isn't science fiction. It's the mathematics of quantum mechanics, confirmed in labs around the world. Yet it's unsettling, because observing the quantum traveler, measuring the system, forces it to pick a single path, collapsing all possibilities into one. The answer is shaped not just by the maze, but by the act of looking. The strength of a quantum computer lies in two phenomena: superposition, which lets it hold many possible answers at once, and interference, which allows it to reinforce correct solutions while canceling out the wrong ones. In the maze, this is like a crowd of explorers who, instead of getting lost, somehow organize themselves. As more join, the crowd becomes more focused. The solution emerges not from brute force, but from a collective pattern that classical logic can't predict. Quantum computation organizes information in ways that don't map onto step-by-step methods. But quantum states are fragile. The environment is always listening, threatening to destroy the delicate superpositions that make quantum computing possible. A stray photon, a vibration, even measuring too soon, any of these can cause decoherence, collapsing the system into ordinary classical behavior. To guard against this, engineers use error correction, spreading information across many qubits in structures called surface codes. The hope is that, by making the crowd larger and more organized, the system becomes more robust. Yet scaling up quantum computers has always meant more noise, more errors, more chaos. The difference between classical and quantum isn't just speed, it's a difference in kind. In a world where observation changes reality and crowds can organize themselves without a leader, the rules of the maze are rewritten. This is the yardstick for measuring progress in quantum computing, not a reason for fear, but a call for wisdom. On December 9, 2024, Google's quantum AI team made an announcement that echoed through the halls of physics and engineering. The Willow chip, a superconducting processor with 105 qubits, had crossed a line that experts had drawn in theory, but never witnessed in practice. The phrase used was below-threshold error correction, and for the first time the phrase belonged not to a whiteboard calculation, but to a functioning machine. The milestone was measured in numbers, not metaphors. Willow completed a random circuit sampling benchmark in under 5 minutes, a computation that, by classical reckoning, would take a supercomputer longer than the age of the universe. But the real headline was not just speed, it was error. The logical error rate for Willow's 7x7 surface code grid dropped to around 2 × 10 to the -4 per cycle, an order of magnitude lower than the physical error rates of the underlying qubits. Each time the encoded grid was enlarged from 3x3 to 5x5 to 7x7, the logical error rate halved. The standard for fault-tolerant operation, set at about a 1% error threshold, was not just met but surpassed. For the first time, adding more qubits did not make the system noisier. It made it quieter, more stable, more organized. The announcement did not come from rumor or a single lab blog. The New York Times, BBC, Reuters, and CNBC all ran stories on the same day. Experts outside Google's labs, from university groups to rival companies, acknowledged the significance. Willow's logical error rate was half that of Sycamore, the previous record holder. The figures appeared in summary plots and bar charts, a logical error probability of 2 times 10 to the minus 4 for the 7 by 7 grid, and physical error rates per 2-qubit gate at just 0.33%. These were not just marginal improvements. They were the kind of numbers that, in the language of surface codes, meant the system had crossed into a new regime. Willow's 5-minute runtime on the random circuit sampling benchmark became a rallying point. In technical circles, the meaning was clear. For a specific class of problems, classical simulation was no longer a practical option. The chip's performance was celebrated not as a one-off, but as a reproducible, scalable achievement. The empirical stake was driven deep, error correction at scale with logical error rates falling as the system grew. For the quantum community, this was a moment of public triumph. It was evidence that the maze could be navigated not by brute force, but by letting the crowd of qubits organize themselves, reinforcing the right answers and canceling out the wrong ones. Yet beneath the celebration, there was a sense of mystery. The numbers were real, the experiments repeatable, but the underlying reason why error rates improved with scale remained partly mysterious. The team knew they had built something that worked but could not fully explain why the system became more stable as it grew. This was not dangerous in a Hollywood sense, but it was scientifically uncomfortable. The act of observation, the measurement that shapes the answer, was not poetry, it was physics. And as Willow's results spread through the scientific world, the call was not for fear, but for wisdom. Subscribe, because the universe is revealing itself in ways we are only beginning to comprehend. The celebration inside Google's quantum AI lab didn't last long. Just days after Willow's error correction milestone, the team confronted outputs that defied every expectation. The chip began returning solution pathways that no one had programmed, and no known algorithm, classical or quantum, could account for the patterns. The lead engineer described it with the bewilderment of a coach watching an athlete invent a move that's never been seen, let alone taught. It wasn't just that Willow was faster, it seemed to be finding roots through the computational maze that the architects themselves couldn't map. Internal discussions quickly turned from pride to unease. The numbers were real, the benchmarks repeatable, but the system's behavior began to drift beyond the boundaries of established theory. A memo circulated among project leads in mid-December. Scaling experiments beyond the 7 by 7 surface code would be paused. Not a shutdown, nothing was powered down, no cables pulled, but a deliberate suspension of the next phase of automated experiments. The chip itself remained cold and operational, running calibration and smaller-scale tests, while the main schedule of benchmark runs was halted. The reason was as much philosophical as technical. The team needed to understand what they were seeing before venturing further. The language of the memo was measured but unmistakable. Scheduled experiments on larger logical grids, 9 by 9 and beyond, were postponed, and all attention redirected to a deeper characterization of Willow's hardware and error syndromes. The phrase systematic verification appeared again and again, echoing a sense of scientific humility. The engineers weren't afraid of a malfunction. They were unsettled by the possibility that the system was organizing quantum information in ways that current theory could not predict or explain. In interviews, project scientists reached for analogies. One likened Willow's behavior to a relay team that, instead of slowing down as more runners joined, somehow handed off the baton with increasing precision. The more complex the crowd, the more focused the outcome. It was as if the act of scaling up, of adding more qubits and more error-correcting cycles, didn't introduce chaos, but instead fostered a new kind of order. This was not a story of hardware failure or runaway AI. It was a moment of intellectual vertigo, building a machine that worked, but not being able to fully explain why. The act of observation, the measurement that shapes the answer, was not a metaphor, it was physics. And when the outputs began to diverge from anything the team could simulate or anticipate, the only responsible move was to pause, reflect, and seek deeper understanding. The pause was not a retreat. It was a recalibration, a recognition that scientific progress sometimes means slowing down when the map no longer matches the territory. Not a reason for fear, a call for wisdom. Subscribe, because the universe is revealing itself in ways we are only beginning to comprehend. Quantum mechanics has always carried a warning. The act of looking changes what you find. In Schrödinger's famous thought experiment, a cat sealed in a box is both alive and dead until the box is opened. For Willow, the box was open and the cat was moving, but the rules it followed seemed to shift with every new measurement. The team at Google was not alone in their unease. Across the quantum research community, the announcement triggered a wave of scrutiny. Physicists from universities in Toronto, Melbourne, and Zurich began combing through the published metrics, looking for signs of experimental drift or overlooked noise. The principle at stake was decoherence, the tendency of quantum states to unravel when touched by their environment. Every lab knows that coherence is fragile, that scaling up the number of qubits is supposed to make things worse, not better. Yet Willow's data suggested the opposite. More qubits, less noise, a crowd that grew more focused as it expanded. Artifacts were the first thing to check. Peer groups requested the raw syndrome records, the unprocessed readouts that would let them reconstruct the error rates from scratch. But Google's public release included only summary plots and a CSV file with limited fidelity data. The absence of full open raw data left a gap. Independent teams could match the trend lines, but not retrace every step. At the Q-Info conference in June 2025, Google's slides showed the same logical error rates, 2 × 10⁻⁴ for the 7x7 grid, physical errors at 0.33%. But again, the details behind the charts remained unpublished. The University of Toronto group ran their own simulations using the published numbers and confirmed that Willow's results were plausible, but could not confirm the precise crossing of the threshold without the syndrome logs. Replication is the gold standard in science. IBM's quantum team, working with their 127-qubit Eagle processor, published a statement that their own surface code experiments reached logical error rates of 5 × 10⁻⁴ on a 5x5 patch, close to Willow, but not yet below threshold at the same scale. They did not dispute Google's achievement, but noted that the field was converging on similar performance. IonQ, using trapped ions instead of superconducting circuits, reported a logical error rate of 2.4 × 10⁻�3, citing Willow as the benchmark to surpass. Each group brought its own approach, but all faced the same challenge: how to maintain coherence as the system grows, and how to verify that the maze is being navigated by quantum rules, not classical shortcuts. Blind runs, experiments where the input is hidden from the device operators, were suggested as a way to guard against unconscious bias. Comparative comments circulated in online forums and technical workshops. People asked whether Willow's scaling was a product of hardware uniformity, software decoding, or something more emergent. Without raw data, every answer was provisional. The scientific method demands not just results, but reproducibility. In this climate, caution is not a weakness. It is a sign of respect for the unknown. The observer effect is not metaphor, it is the backbone of quantum reality. As Willow's outputs continued to puzzle, the community's response was measured, methodical, not a reason for fear, a call for wisdom. Subscribe because the universe is revealing itself in ways we are only beginning to comprehend. The surface code forms a lattice, each qubit precisely placed on high-purity silicon, capped with titanium nitride. Some qubits store quantum data, others are ancilla qubits that monitor for errors, never touching the information itself. Picture a city grid where each resident quietly watches their neighbors, passing coded hints to a central hub. Ancilla qubits run parity checks on overlapping groups, cycling rapidly to produce syndromes, signals that suggest where errors might lurk. The quantum state remains hidden, inferred only through shifting patterns in these reports. Decoding falls to a specialized hardware engine built on field-programmable gate arrays, which sifts through syndromes in real time, reconstructing likely error paths and correcting them before the quantum state slips away. Speed is critical. Every microsecond trimmed from decoder latency preserves computation. Beneath it all, the substrate, now sapphire-backed silicon, must be nearly flawless, as imperfections spread noise across the grid. Tighter fabrication tolerances have pushed coherence times higher, suppressing crosstalk. As more qubits join, the system grows more ordered, not more chaotic. Yet with scale comes organized opacity, a mechanism that works, but whose logic becomes harder to untangle. At Google's quantum AI lab, uncertainty took on a new shape. Willow, their quantum chip, brought together two black boxes, a quantum optimizer buried deep in the hardware, and a machine learning loop tuning its every move. Alone, each system was hard to interpret. Together, they created a process even its designers struggled to follow. When Willow produced results that defied explanation, the challenge was not just accuracy, it was traceability. Classical audit tools such as trace logs, reproducible pipelines, and benchmark tasks were built for systems where every step could be tracked. Here, outputs hinged on interference across 100 qubits, the timing of syndrome measurements, and the unpredictable quirks of machine learning algorithms. The logs captured only fragments. Policy experts and ethics advisors raised alarms. How do you trust a system whose logic cannot be reconstructed? Some called for exhaustive trace logs, recording every syndrome and calibration. Others suggested blind benchmarking to test the system's honesty. Yet as complexity grew, even these safeguards faded. The risk was not just error, but compounded opacity. Knowing what happened became as uncertain as the answers themselves. What actually broke was not the hardware, nor the code, but the way the field understood the relationship between scale, noise, and computation. For decades, the scaling intuition was clear: add more qubits and you multiply your problems. Every new qubit is a new channel for noise, a fresh opportunity for decoherence to unravel quantum information. Every model, every textbook, every simulator agreed. Error correction would only work if you could keep physical error rates below a fixed threshold, and even then the best you could hope for was to tread water as the system grew. Willow's results did not just bend this rule, they snapped it. Logical error rates fell as the grid expanded, contradicting the very mapping between physical noise and logical stability that surface code theory had assumed inviolable. The experiment left the research community staring at a system that seemed to organize itself more cleanly as it became more complex, a crowd that grew quieter as it swelled. The phrase that echoed through technical memos and late-night calls was simple: the map no longer matches the territory. What Willow revealed was not a malfunction, but a gap in the collective understanding, a place where the rules so carefully drawn failed to describe the world as it was measured. This is not dangerous in a Hollywood sense, but it is scientifically uncomfortable. You are building something that works, but cannot fully explain why. Not a reason for fear. A call for wisdom. Subscribe because the universe is revealing itself in ways we are only beginning to comprehend. Today, entire research protocols remain paused, not from fear, but from humility. Willow's logic didn't just solve mazes, it found new rules for the maze itself. When a system grows more ordered as it expands, scientific caution is not optional, it is essential. This is not danger in the Hollywood sense. It is the universe refusing to fit our maps. Not a reason for fear. A call for wisdom. Subscribe. The universe is revealing itself in ways we are only beginning to comprehend.